A calorimeter is an isolated system that is used to measure the heat exchange in a chemical reaction. In the next few videos, I'm going to be talking about the different types of calorimeters and how they are used to measure the heat exchange in a chemical reaction and how we can solve problems using the data obtained from calorimetry. In this video, I am going to be focusing on two fundamental concepts that are necessary for you to understand in order to be able to do problems involving calorimetry and calorimeters. These two very important concepts are specific heat and heat capacity. All calorimetry problems and all calorimetry experiments rely on either specific heat or heat capacity. So it's necessary that you have a really good understanding of these two concepts. Specific heat we abbreviate with a lowercase s, and heat capacity we abbreviate with a capital C. Specific heat and heat capacity are two concepts that students a lot of times have a hard time distinguishing from each other. This is because they are very similar concepts. The specific heat is the amount of heat, and this is typically measured in joules or kilojoules. It is the amount of heat that is needed to raise the temperature of 1 gram of a type of substance by 1 degrees Celsius. Heat capacity, on the other hand, is the amount of heat, also typically joules or kilojoules, the amount of heat that is needed to raise the temperature of a specific object again by 1 degree Celsius. So as you can see from these two definitions, the definitions are very similar, and this is why a lot of times students have a hard time distinguishing specific heat from heat capacity. In particular, specific heat and heat capacity are different only in terms of what they are describing or what they apply to. Specific heat is a number that applies to a particular type of substance. For example, specific heat maybe applies to aluminum, the type of substance aluminum. Heat capacity, on the other hand, applies to a specific object. So the heat capacity maybe applies to a particular 1 centimeter cubed block of aluminum. So the specific heat applies to just a type of material, whereas heat capacity applies to an actual object with a specific size and a specific mass. We can use a specific heat to calculate the heat exchanged in a chemical reaction, heat which, as you know, is abbreviated lowercase q. The specific heat times the mass of the object times the temperature change that is observed by that particular object gives us the heat exchange in a chemical reaction. And in this equation, the little m represents the mass, which is always going to be in units of grams for this particular equation, and delta T represents the final temperature minus the initial temperature, always in units of degrees C. Specific heat, which is a constant, which will be provided to you as part of the problem. Heat capacity has a very similar looking equation, Q equals C delta T, where Q is the heat, and C is the heat capacity, and delta T, the same thing, temperature final minus temperature initial in units of degrees C. So, like I said, it can be very confusing for students to know when they should use this equation, which I like to call SMAT, and when they should use this equation, which I like to call CAT, and exactly what the difference is between specific heat and heat capacity. But hopefully in the next few videos, all of this stuff will be cleared up for you. Before we jump into learning about how to use the data obtained by a calorimeter, let's just do one practice problem here, calculating how much heat is required to raise the temperature of 150 grams of water from 20 to 80 degrees Celsius. And it's giving us the value of the specific heat for water. Since we've been given the value of the specific heat for water, that's a big hint that we should be using the Q-SMAT equation. Q equals S M delta T. The problem is telling us that the value of S is 4.184 joules per gram degrees C. We want to multiply that by M, the mass of water, which in this problem it tells us 150 grams. And then we also want to multiply by the temperature change. Let's do a little side calculation down here. The temperature change is going to be the final temperature minus the initial temperature. Problem is telling us that we are going from 20 to 80. So our final temperature is 80, our initial temperature is 20, and our overall delta T temperature change is 60 degrees. If we do the math on this and work this all out without thinking about significant figures, we get 37,656 joules. That's a pretty big number. And a lot of times these numbers are expressed in units of kilojoules rather than units of joules. 1 kilo is 10 to the third joules. And if I turn this into, let's just say 2 sig figs, this would be 38 kilojoules. And again, this problem is asking, this answer is telling us 38 kilojoules of heat are necessary to raise 150 grams of water by a 60-degree temperature change.